Earth just grew to the size of Jupiter. You're somehow still alive, but you can barely lift your head under 11 times normal gravity. The moon is being dragged into a brand new orbit. The atmosphere is crushing itself flat, and every inner planet just noticed a new gravitational heavyweight packing more than 4 Jupiter masses. So what hits first? The collapse, the cooking, or accidentally rearranging the entire solar system? To trace this scenario accurately, we must lock in a few rules. This is a physics thought experiment, not a natural planet formation event. We are inflating Earth's radius by exactly 11 times, matching Jupiter's massive 71,000 kilometer span while holding our current average density completely fixed. We will also keep our 24-hour day. Because volume scales three-dimensionally, this expansion multiplies Earth's total volume by over 1,300 times. And since we kept the density unchanged, the planet's mass also skyrockets by 1,300 times, making our new home over 4 times heavier than Jupiter itself. Surface gravity scales up linearly with radius, making everything 11 times heavier. The moon, which used to look like a respectable partner, now looks like a stray marble orbiting a beach ball. We basically just ordered the ultimate planetary upgrade package, but the cosmic delivery fee is about to be absolute chaos. At 11 times normal gravity, the simple act of existing becomes an immediate physical crisis. If you weigh 150 pounds on our original Earth, you now register at over 1,600 pounds. Your bathroom scale would immediately shatter, or at the very least, require years of intensive therapy. Standing up is no longer a physical motion. It is a full-body medical emergency. Your cardiovascular system has no baseline for this load. Because blood is now 11 times heavier, your heart cannot pump it upward against the crushing gravity. Within 5 seconds, blood drains entirely from your brain, causing tunnel vision, rapid blackouts, and complete loss of consciousness. Before you even pass out, your muscles fail. Getting out of bed is completely off the table, and taking a single step up a staircase requires the physical output of an Olympic powerlifter. Lifting your phone to call for help feels like hoisting a heavy slab of concrete. This structural collapse quickly spreads to our built environment. Cars collapse onto their axles as suspensions snap, making driving an extinct concept. High-rise elevators experience instant cable rupture, their steel lines snapping as the heavy cabs resign from their jobs on the spot. Even reinforced skyscrapers designed for normal loads buckle at the joints, their thick steel columns bowing under the sudden weight of the 80 floors above. The natural world fares no better. Massive oak trees suffer instant xylem and turgor failure, their water-carrying vessels collapsing before the heavy trunks snap like dry twigs. Land animals are pinned instantly to the dirt, unable to support their own limbs. Even the skies clear out permanently, as the crushing weight forces every bird into an abrupt, involuntary retirement. The atmosphere itself cannot escape this massive downward pull. Gravity squeezes the entire air column, pushing the atmosphere into the absolute front row right against the dirt. This compression drives surface air pressure up to a crushing 10 times normal, transforming the sky into a thick, heavy soup. In this dense environment, the physics of flight are completely rewritten. Every commercial flight plan instantly becomes a permanent retirement notice, as wings designed for our old thin air are utterly outmatched. Sound now travels faster and further through the crowded molecule highway, while clouds hang low, dropping a constant heavy drizzle of tiny, shattered water droplets. Below, the oceans spread incredibly thin across a surface area over 100 times larger than before, averaging just 30 meters deep. Under this immense downward loading, these shallow global seas turn into hyperactive, high-speed lanes, driven by accelerated currents that completely reshape planetary water dynamics. Deep beneath the surface, the planet itself begins to buckle. This massive new Earth cannot remain a simple, scaled-up copy of our old world. As gravity compresses the planet's interior, internal pressure skyrockets to several terapascals, triggering extreme self-compression and generating intense heat throughout the mantle. The solid ground we walk on cannot withstand these forces. The sheer weight of the rock above crushes the lower crust, forcing minerals to collapse into denser, exotic high-pressure phases. Global-scale earthquakes rip through entire tectonic plates, shattering the lithosphere. Exactly how this unfolds depends on how fast the planet can deform, leaving some scientific uncertainty. But the physical limits are clear. Under this extreme heat and pressure, the crust and mantle undergo decompression melting. Entire cities, from Paris to Shanghai, lose their solid foundations as vast subterranean magma oceans form. Instead of a stable, familiar rocky crust, the planet's outer shell softens into a shifting, molten expanse. The very shape of the Earth is changing from within. This colossal gravitational power immediately drags our quiet cosmic neighbor, the Moon, directly into the drama. Because our planet is now 1,300 times more massive, the Moon's current orbital speed is suddenly far too slow to keep its comfortable distance. Computer models show the Moon being pulled onto a tight, highly elliptical, inward spiraling trajectory. It's like the Moon suddenly decided to become the ultimate clingy roommate, refusing to give us any personal space. This rapid inward drift sets off monstrous tidal forces. Even with our global oceans spread incredibly thin, the gravity of this closer, faster pairing would whip those shallow waters into towering supertides, regularly drowning entire continental interiors under kilometers of rushing water. But how this orbital dance actually ends is a matter of computer simulations, not destiny. While some integrations suggest a catastrophic collision after hundreds of millions of years, the long-term physics of this altered system are far too chaotic to predict with absolute certainty. At over 4 Jupiter masses, our transformed Earth immediately becomes a major gravitational disruptor in the inner solar system. The nearby planets and the asteroid belt now find themselves in a highly unstable environment. Earth has essentially become the ultimate gravitational bully, and the celestial HOA is completely powerless to stop it. Long-term N-body simulations reveal that Venus, Mars, and Mercury face severe orbital distortions over millions of years, with some altered orbital runs suggesting outright planetary ejection. The asteroid belt is a primary target for this disruption, likely being cleared out entirely as its rocky fragments are flung into deep space or toward the Sun. Even Earth's own orbit around the Sun becomes part of the stability problem, beginning to wander and making the entire system's future highly unpredictable. Yet this extreme mass does not make Earth a star. It is far below the deuterium-burning threshold required for thermonuclear ignition, and it is nowhere near collapsing into a black hole. Instead, these simulation-based runs present a range of chaotic possibilities rather than a fixed destiny, leaving the long-term stability of our solar system as an open question. Surface survival on this bloated world is a flat-out impossibility. Even hiding underground presents a structural nightmare, as standard subterranean shelters would immediately collapse under the weight of the self-crushing rock above, requiring reinforced concrete vaults over 3 meters thick just to stay intact. The only viable escape hatch lies in the sky. Massive, rotating space colonies like O'Neill cylinders could spin at 1 revolution per minute, generating a comfortable, simulated 1G environment for long-term survival. Of course, this all depends on timing. If this planetary growth spurt happened instantly, the story ends. But if the transition were gradual, humanity might just survive by moving upstairs, proving that when your planet gets too heavy, the best engineering solution is to simply walk away from it. Earth's perfect size is the unsung hero of our existence. We don't need to expand to be extraordinary. To see how our actual world shines across the cosmos, watch AstralNext HQ's What Earth Looks Like from Every Planet in the Solar System.